When we try to go to the Moon in Kerbal Space Program, you'll quickly realize that we can't just take a straight shot there. There's a few reasons for this besides inefficiency, and it's an elegant solution when you look at the science behind it all. To show you what happens, I'll set a course to go straight up towards the Moon, and we'll see what the consequences are from that. As you can see, we're doing pretty well so far. We have SAS going radial so that we're going straight up towards the Moon. But then we start to tip down without control. And we're slowly turning into a missile hurtling back towards Earth. And it's looking all over for Jebediah here, because nobody wants to be inside a missile. But luckily we can just bail him out and he'll avoid the big explosion. So, Jebediah is fine. So what happened? And what if we had a perfect rocket that could do this? The Moon moved away from us, right? So why does that happen? Since isn't the Earth just spinning and the Moon moves because of that? Wrong. The Moon orbits around us. Ancient Babylonian scientists discovered this, but Isaac Newton explained why. He called it the falling moon problem, where the Moon is constantly being pulled down to Earth by gravity, but its sideways speed lets it move in an orbit around the Earth. He derived the force of gravity and we can get Kepler's third law. And how can this help us? We can find the time it takes for something to orbit the planet off its radius, and we can get a Hohmann transfer. Because we calculated Kepler's third law, we know the exact duration of this trip, and so we can get the Moon's orbit, but we don't know where it's going to be, so we need the nifty phase angle. We do some math, and I'll show you a quick video to see how everything works. We get the semi-major axis, the eccentricity, and calculate the ellipse. Then we can use the Vis-Viva equation to calculate our orbital velocities all around the ellipse. We do some more calculations for the first delta V and second delta V, and then we can calculate where the Moon's going to be based off our speed. Turns out it's going to be 110.88 degrees. So I'll show you how it looks like when I try it in Kerbal Space Program, but I'm new, so I don't do very well. So, using the 110 degrees rule, we managed to get pretty close to where the Moon is supposed to be, with some adjustments needed. I didn't use my fuel efficiently, so I'm kind of stuck in space right now, but here's some notes. You want to burn at the periapsis for the Oberth effect, and you should be at 110 degrees from where you are in orbit, and don't do what I did. Now it's time for mini computer coding. First, we're going to make a planets dictionary that holds the data for everything. We'll put in the radius, the semi-major axis, the mu, and the color, with mu being the gravitational constant times its mass. Then we'll make a method to generate ellipse points for our plot, and we let theta be a collection of points from 0 to 2 pi, exactly 200 of them. Then if it's a transfer orbit, which it should always be as we hardcode it, we only do half. Then we use the polar ellipse equation here, r equals a bunch of stuff, and then we can let x and y be given from that. To make the page itself, we need forms on the left and a plot on the right, so we do horizontal box layout. Then we make a combo box to display what we want of our planet selector, giving Mun and Minmus as our options, after making a group box to put everything in together. After that, we can give a mission readout, giving data like the phase angle, delta V's, and such, letting us put in whatever we want to know about the mission. Next we make our figure, and we want it to be square, and we gotta do the 1, 1, 1 thing like every other time when we're adding a subplot. So once we add those widgets, the main layout will be good. Now we just make a method that updates everything if we change the destination, and then it simply calculates a new Hohmann for us. Oh, but it looks like I typed Hoffman instead. I gotta fix that. So to calculate the Hohmann, we take in all our data and use the math I showed y'all earlier. And that's going to take a bit for me to type out. Next, we make a curve in a circle with r divided by 2 so that it shows us the orbit lines, and then we now get to make the ellipses for everything. So LKO stands for low Kerbal orbit, and that shows us how the spaceship is going to circle around Kerbal before we send it off. The rest of this is pretty easy. We have all the math down, so that's really it for making it. We just have to type out all the ellipse points and everything else with it. So as we're finishing up here with setting up the settings for the plot, we'll show you the result, and then our mini computer will be finished. We just need to set up the hardware for it. I guess we're not done yet. I still have some stuff I'm typing out. There we go. So I'll uncomment the add widget for it, and we'll see how it looks.